So, good afternoon, everyone. Thank you, everyone, for joining. Today is our session number 14, and we have the pleasure to have as a speaker Dr. Shervan Gharari. He is a research associate at the University of Saskatchewan in Canada. The title of the paper that we are going to discuss is Understanding the Information Content in the Hierarchy of Model Development Decisions, Learning from Data. So thank you everyone and welcome Dr. Shervan.
Thank you very much. Should I start like sharing the screen or we wait a couple of more minutes? What do we do?
I think it's a good time to start.
Excellent. So, yeah. Yes. Start sharing. And everybody sees my screen, I hope.
Yes, that's good.
Excellent. Maybe I minimize this. Good morning, good afternoon, and good evening, depending on where you are on the planet. Thank you very much for giving me the opportunity to present this work that was recently published in WRR. And just to say that my name is Shervan Gharari. I'm from the computational hydrology team. Currently, I'm working with a group of Professor Martin Clark on continental scale modeling. And my major interest at this moment is implementing lakes and reservoirs in continental scale routing model, which is missing in the air system modeling, and it's something which is not really well explored at the global scale. Well, today I am going to talk about something different, this paper that actually started long ago together with Hoshin, and finally came to an end, and hopefully we will continue future work, and I'm very happy to hear your feedback on the work that might help us to move forward. So a brief background, and for doing that background, I just go and took some slides from Hoshin paper, Hoshin presentation for his doctoral medal lecture at the EGU 2014. And of course, Hoshin, whenever you want to add something, please contribute. So the idea is that when we have a process-based working model, which includes input, output, and state variables, which are defined by X, we should have an interconnected structure from these states and fluxes, which are connecting the input to the output. But the problem is that to get a working model, which I come a bit later on that, is we should know the parameterization, which are specified by P. And there are assumptions on the form of the P and how it should be. And actually, there are a lot of discussion on that. So which one is right, which one is not right, and what should we make those functions dependent on. It can be dependent on one state variable, or like this one can be stated on the two state variables. But what if we could just explore basically the impact of our decision to just make this net of states without any strong assumption on the parameterization and the parameter values? So that was the question we were after, and Hoshin was asking. So I had the opportunity to meet Hoshin to spend time in University of Arizona from November 2013 to I think April 2014 before coming back to Europe and to this EGU, I remember. And the idea that we come up with was that we create randomly generating functions which have some specific shape and form and assumption. And we explore which of these functions are the best for a given substructure. And I should also mention that these ideas that were developed over the past few years, they are rooted in these studies that I'm mentioning here, and also some other studies that were very helpful in basically building what we already built. And 7 years passed, nothing happened. And finally, almost after 7 years, on the anniversary of 7 years of Hoshin Dalton Medal Lecture, we had this paper finally accepted and out. And the paper itself has a long, basically history. We maybe spent like 2 years with Hoshin just to write it. And I think addressing the comments of the co-author took us maybe 6 months or even more. And there was a lot of discussion going on, and we revisited a lot of text, maybe the introduction here, the section 1, which is very well written. And I suggest you to read, and especially for students might be a very good text to read. Maybe was rewritten like 10 times or more. And we had a long also review process with 5 reviewer, 3 rounds of revision, which again, a lot of part of this paper was heavily modified. But that's out now. I'm going to talk about what we have done. The objectives of this work is to lay out an alternative way of thinking of process-based model development as hierarchy of hypotheses, map the interaction of the hierarchical decision by modelers in building process-based models, explore the interaction of the hierarchical decision and the modelers. So the second one is basically the modelers will make decision. We want to know the impact of one decision on the other one that they make. The third one is actually understanding of how the modeler interact with these decisions. Explore the effect of expert knowledge on constraining the plausible solution, on the dialogue between experimentalists and modelers, which are basically lacking in my point of view in the field. Propose an active role for process-based modelers to apply machine learning techniques to search for hydrological laws if that exists locally and globally, which I think that's very important for us as a process-based modeler, because the way I see things are going is that processes are given less and less attention, and the solutions are given more and more attention. So if somebody has a solution, doesn't matter how he or she arrived with, just because it fits better, might be prioritized without really digging deep into the processes. So we hope this work will change that a little bit and make the process-based modelers to actually contribute more than what they are doing now in this shift. I start with a very simple explanation or very simple question. What is a model? An abstract and simplified representation of real system, a tool for extrapolation and interpolation of our knowledge about the real system, spatially and temporary, and a platform where our information knowledge about the system is loaded or compressed. But the question is that how do we do that? Maybe in 100 different ways. Traditionally, how do we build a process-based model is based on this diagram, which is often taught in hydrological modeling. Is first we think about a perceptual model, make a depiction of it, then we change it into the conceptual model, which are including the equations, then getting the code into the computer, so procedural model, and then the model calibration, which can have various different forms, can be manual calibration or automatic calibration, and finally model validation, which is, in my point of view, for a lot of model at larger scale are almost impossible. We would better do just model evaluation, actually, what we do with something like extensive testing, like bootstrapping, changing of the calibration validation time, etc. And model as assemblage of hypotheses, that's what I'm going to talk today about, is that actually the decision that we make can be categorized in 4 different levels. The first level is that the conservation principle and system diagram. So I decide about what system I want to model. That's a basin, that's a catchment. And then I decide about what conservation principle I want to hold. I want to have the mass balance, energy balance, and therefore I also know the input output to the system, and also in more complex form, the boundary condition of my system. The second step is system architecture, in which I decide about the states variable that link the states in the system through fluxes that can map input variables to output variables. The third step is process parameterization. So all of these fluxes that we have specified, which can be specified differently, can have a function. And these functions can be dependent on many things. For example, transpiration can be dependent on the storage, for example, leaf area index, temperature, vapor pressure deficit, if we have it as an input, etc., etc. And finally, we decide about the parameter values. If we do everything right from the first step to the last step, we should progressively reduce the plausible space of the model simulation. So the lightest blue is the conservation principle and system diagram. So we come from infinity to here by just assuming the system diagram and what is going inside, outside. And actually, this is the effect of the forcing, which is pounded on the system. The second step is the system architecture, and then we do the process parameterization and then parameter specification. And hopefully, if everything goes right, we should converge around the observation. Maybe for some reason, for some regions, we basically won't be able to capture, which is the bias in the model, which is also very hard to capture. But at each level of the steps, we are adding information, and this information is nothing else than change of uncertainty given the context, which the context here is, for example, the output, which is the stream flow. It can be any other thing. If we draw the diagram of the previous slide into a more systematic way, we can have 4 different layers of decisions that we have to make a working process-based model. And all of them are basically equally important to get a working model. And there are top-down and bottom-up approaches. In the top-down approach, we mostly emphasize on the upper part, and then the lower parts are inferred. In the bottom-up approach, we mostly emphasize on the lower part, and the upper parts are kind of emergent. For example, if we decide about that we want to I don't know, solve the flow of water between 2 wells, and then we decide about the parameterization, let's say Darcy, and the parameter specification, we kind of are, and then we have a, let's say, a implicit, yes, yes, we can solve that implicitly. then we can basically say that we are deciding about the upper two levels of the modeling. So question that we try to address here, okay, maybe I should explain something else. There are other hypotheses that are outside of the modeling hypothesis. So that is the input uncertainty hypothesis and system response uncertainty hypothesis. This can be a stream flow, what we usually calibrate our model on, which I explain a little bit in the next slides, and the performance metric hypothesis. So these are also hypotheses. I want to calibrate my model on KGE or Nash-Shotcliffe or in a million different ways. And there is other source of information, which are basically, I would say, they're kind of tacit knowledge in the sense that it's very hard to quantify them. It depends on the background of the modeler. I'm an engineer. I would model differently from a people. Yeah. Hello?
Yes, speak.
Okay. So, for example, I'm an engineer and I would model differently than a person coming from, for example, geography background or a mathematics background. That's very important, but again, I am not sure how to really assess this. Maybe we can discuss this during discussion. The question that we try to address here is that how is information encoded into the model at each level of model building? So again, back to this chart, and most of the emphasis that the modeling world is basically emphasize on is the parameter specification, a lot of calibration. So we get a out-of-shelf model, maybe adjusted specifically. So the other levels are already fixed and we just calibrate our model. Recently, there are more emphasis also on the system architecture, like more flexible approaches for the modeling, especially catchment scale conceptual models. They are lacking in larger scale modeling and land surface modeling. In land surface modeling, recently we have the multi-parameterization like NOAA-MP and SUMA, which can also touch on the system architecture hypothesis. And yes, mostly our knowledge, which we call our knowledge, is coming from the inference based on the system response uncertainty hypothesis, or basically response hypothesis, or it can be stream flow, projected into the modeling hypotheses. And maybe I told this to some other colleagues, and they said it's really a strong wording, but we should never, ever mix the hypotheses here and the input uncertainty hypothesis and the output uncertainty also. So the efforts that are basically claiming to know the input uncertainty or output uncertainty, error distribution, or basically perhaps the residuals, etc., together with the model are should be taken with basically a grain of salt, because when we do this inference, it's like calibration, and when we do calibration, whatever we do is dependent on the input forcing, modeling hypothesis, performance metric hypothesis, etc., that we have. And if we change that, our perception might totally change. So although we zip, but we zip given the hypothesis that we have in our model. So the second question is the form of process parameterization equation. Which form are appropriate for what system architecture? Because often these process parameterization equations are very rigid and we don't really think about changing them. Let's say the function of transpiration is URVs. we are fixed with the others. We don't really question much about it. So how do we do that? That was the contribution of this work also, is that traditionally we have conventional rigidly pre-specified parameters equation. So the form of the parameterization is clear. We only change it by changing the parameter value. But however, we can have the minimally restrictive process parameterization equation, which allow us different forms, and it's obey some minimal rules that we put on them. For example, it should be monotonically increasing, for example. And that, by doing that, we reduce the emphasis on the parameter value and parameterization, which in turn help us to understand the effect of the higher level of the decision we make in the system diagram and subsystem architecture. So similar to the calibration, that we reduce the emphasis on the parameter value by relaxing the boundaries of a parameter value, we can exactly do the same things for the process parameterization by relaxing the assumption on the process parameterization equation, and then with more confidence say that the changes in the uncertainty is coming from level 1 and level 2. So how do we build this minimally restrictive process parameterization? There are different ways of doing it. I'm not saying that this is the best way of doing it. And I am sure, basically, I've seen that there are a lot of discussion how to do that. But for now, we just fix the starting point and ending point. This is 1, and this is also 1. So align 1, 1, and then between the two, we pick a random value for the X and a random value for the Y. And then we break our line, and then we do exactly the same things here and here. So we have more points, and then we continue to get some sort of piecewise function, which are basically starting from 0, 0, 0, and ending at 1, 1. And after 1, we assume that the function is constant at 1. And then we can scale it to give it a meaning. So we have also parameters, which are the lower bound, the higher bound, and the scale, which is some sort of scaling this 1 to the storage, like 40 millimeter. And then it means that at the 0 millimeter for that bucket, that function is 0.2, and at the higher value, that function is 0.8. And we can also project that into a logarithmic space if we would like. Again, this is how we have done it. It can be done in many different ways, and that's something which we can discuss and can be an avenue to explore for the future. The other very important, in my point of view, aspect of modeling, which have been totally ignored, I've never seen such a thing like that, is how uncertain are the, or I have never seen as a study that really looked into it for the process-based model, let's say, is that how uncertain are the process parameterization equation form inferred from the data. And what we are trying to say is that there are functions, the blue ones, which are maybe a priori fixed, and we just change them by changing the parameter values, but maybe there is a existing line which satisfy our basic assumptions, and it can actually fit the data better. And what would that be? The other aspect, which is also not very much, I've never seen that to be really discussed at the process parameterization level, is the activation level of a parameter, of a parameterization. So I can have exactly similar process parameterization, but this process parameterization can be activated differently over the course of the simulation. And some part of them can be not activated at all, which is interesting. So maybe I'm just using 10% or 20% of actual function that I think is basically the right function, but actually it's only 20% of it which is working, and from that 20%, maybe only 5% is actually working, maybe more than 90% of the time. And so after each simulation, we have to refine our understanding of the minimally restrictive process parameterization. It can be done on also conventional process parameterization, that we should check which part of it was active and how that changes over different simulation, which again, this reflects the forcing and reflects other decisions that we make in our modeling decision. And another very important aspect, which again, not really to my understanding explored, is the behavior constraint. This relates to the tacit knowledge also, which I specify. And again, most of our information in the modeling, it's a catchment scale modeling, larger scale modeling, when we want to do the modeling at the high spatial and temporal resolution, comes from this behavior constraint and the assumptions that we put on the model, the hierarchy of the model. How that evolve and change our perception, and are they important or not, or which one are they important or not, or how do we build them? It's rather difficult. I would say this is the holy grail of hydrology. So to start our experiment, we have two experiments which I will explain here. We come up with a generic bucket. The generic bucket is a bucket that can satisfy a couple of processes. The first process is absorption, and basically bypass. So part of the water can be absorbed, part of the water can be bypassed. The other one is release. Release is basically a function of the storage, and the other one is depletion, which is a function of a storage and a depleting variable or constant. Basically, with these three, we can build almost all the conceptual models that we have. So like HPV, Flex, J4J, even we can approximate the splitter by them. For example, a snow degree day factor is something like that. We have a storage of snow, and this is the difference of temperature, which how much the system is ready to be melted, or how much energy is given to it in a very simple form. And of course, we can make this more complex for more complex model if needed. And using them, we can come up with three basically core model structure, model S1, S2, and S3. S1, all the water comes in, like as precipitation is absorbed in the system, it's only transpired and left from the drainage. S2 is all the water comes in, is either bypass or absorb, and there is no leakage. We only can deplete by transpiration. And S3 is a combination of S2 and S1, so I can actually bypass, or I can actually also leak and transpire. We can add interception. We can add one routing pathway and two routing pathway to our model. So we can basically, by mixing this level and this level, we can build a model. For example, I1, S2, R2 in a simple form. So it means that I have interception, my core model is S2, and I have two routing component. And then I come up with some very simple behavioral constraint. For example, my model should not accumulate water, should not have a trend in storage. I should not have a large inactive storage. The fast and the slow component should really be fast and slow component. For example, if I draw the functions, the slow component should not overpass the fast component for a given storage. And I can also put assumptions. For example, in this case, the experiment 2 that is located in Luxembourg, I can say something about the interception and transpiration, the ratio, or I can say something about the runoff. And if these models are very simple, if they become complex, if we go to the discussion, I have it in my supporting slides, we can put much more complex constraint and then search for those constraints as well. But again, really coming with a good constraint is not that easy, because it's kind of some of these constraints might look trivial. So if you talk with a modeler or experimentalist, they might say, to an experimentalist, they might say they know a lot, but then when you say, okay, formulate some of these for us to really put in the model, they might come up with very general understanding of the system. So experiment 1, I have 3 buckets, which are only differs in how the input output are linked. First of all, I basically run them with a synthetic data, which goes up and down every 2 weeks or something like that. As you can see already, there are differences in how the storage respond just by different structure that we have or different linkage that we have. For example, the model S3 is easier to deplete because we have temperature, transpiration, and then we have the drainage, and also there is less water goes in because there is a lot of water bypass, so it hardly gets to the higher storage value, unlike, for example, S1 or S2. And the red is the simulations that they do not obey the constraint that I just talked about here. And the blue are the one that obey the constraint. So if we zoom in into one of these guys, for example, look at the soil moisture and the behavioral one that are obeying the constraint. So it's clear that, for example, S1, because it's a kind of a leaky bucket, so it has a exponential decay here. So if we put it on a log-log or semi-log axis, it would be a line. This is looks more of the decline looks like a line because transpiration is more linear. And in S3, it's a combination of both. This is the same with the stream flow. For example, S2 has a very sharp reaction. S1 has a very long tail because S1 has a very long tail, and S3 is a mix of both. So by combining the two, we can get more flexibility. And this is for evaporation, which I just put here for just a visual comparison. And we can continue, and we can then look at the functions. This is the bypass function, and the red again is all the simulations, and the blue is the simulation that satisfies the constraint. What I'm looking here, what I'm showing here is the only active part of this parameterization. I chop off the part of the parameterization that is not activated during the simulation. So for example, you can see that just by making the structure more complex, my bypass function, the plausible bypass function, is changing drastically. This is the case for depletion and evaporation. Here in this system S1, I can drain my system with another process than the transpiration. So my transpiration is kind of not very well identified in comparison with the case that I only can deplete my system with the transpiration. And again, if I have more structure that allow me to drain, so I have less of the identifiability of the transpiration function. And here is the drainage, the Q drain, and the parameterization for that. There is I didn't show it in this paper, but there is an interplay with the two. So when the drainage is higher, this transpiration mode is lower, of course. And when I don't have any depletion, my transpiration become more identifiable, or basically I would be more certain about its shape. So this is just to say that a simple change in the structure will change basically everything. So even if I say there are physical meaning for example, drainage, and this based on the physics, it should have this parameter and this formula, it doesn't hold if I change the modular structure slightly. So the other experiment is based on the real case data we have done for Luxembourg. I think it was the VAR catchment, and this is basically quantifying the information content we are putting at each level. And for this study, we didn't use Shannon entropy for the information we just used as the bandwidth of the uncertainty to just make things simple for the readers. But it can be done on any basically entropy measure as well. So the light blue is nothing else that are information from the conservation principle and forcing. So what does that mean? Means that using the minimally restrictive process parameterization and using the elements I explained earlier, I make as much as model as possible. I think maybe 15 or 12. And then I simulate to the level I can with the minimally restrictive process parameterization. And the 595% interval of them shows this blue line, really light blue band, which basically tells me with this structure, with this constraint, and with this forcing, I can come from infinity to here. The darker blue is when I choose a specific system architecture out of those multiple system architecture. So here is model I1, S2, R2. So I have interception and I have two pathway. Then I can make it more specific and then put some rigid process parameterization, which reduce the possibility even more. So, and then I can come up with some sort of inference, and let's say I can pick up those basically simulations that create the Pareto front based on the KG components. And that would be the darkest blue, and the red is the observation. You can see sometimes they don't have overlap. That is simply a technicality issue because I cannot easily create a lot of simulation so that I can cover the whole space. And the number of simulations here are kind of limited. But if I would do millions and trillions of simulation with very good search over the space of the minimally restrictive process parameterization, this gap should not be there. So just to say why we see this. So I continue with creating one model S2 and then combination of the other models. So I just compare model S2 with one routing bucket, S2 with two routing bucket, and with interception. And with minimally restrictive process parameterization, these are the KG component with mean, I think standard deviation, and this is correlation. And as you can see, as we put more structure, we get closer to the best performance, which is 0. If we do the conventional process parameterization, most of the model will come closer to the best performance. And basically what is here is that from infinity to here, we are coming by simply a structure. And from this point of the performance to here, we are coming by the assumption and the process parameterization. So that's how strong it is. And the other thing is that we always, or most of the time, have good performing models for this case, which means that if I really want to calibrate, I wouldn't see probably much difference between all these models. And basically, I pollute my information from the model so much that I'm not able to distinguish between them. I'm sure you can explain this in much better scientific terms. And then if I merge the uncertainty that I get, which are basically simply this simple measure of the band or the uncertainty of 90% interval and 10% interval for these 4 models and the average performance, I can map where I'm moving in this performance uncertainty space. So what I want to say is that if I pick this model and minimally restrictive process parameterization, I have all this plausible space. And if I do strong process parameterization, maybe I have this space. And most of the uncertainty studies, most of the sensitivity studies, most of the discussions we have on the modeling in the, practical modeling in the conferences, and most of the disagreement are just because everybody is picking one part of this gray, probably rectangle, and talking. And then we can come up with some calibration, narrow it down. Again, we should not really fool ourselves that we are reducing this space in the sense that we are producing knowledge. We don't actually produce knowledge, we just reflect what we know from the output into our hypothesis. And then finally, we can get to a point B where we have one solution, which is this is done often by experimentalists. They just come up with the one solution and the uncertainty is 0 and with some performance, some acceptable performance. So again, back to this, that's why I think it's really important for all the studies to really clearly map what they are doing and the initial hypothesis, what they infer, and how they went in and out of these red boundaries, not to express those findings as really scientific findings, because they're just calibration. We may discuss this later during discussion. Maybe I have a very strong opinion in it. Anyway, the other factor I want to talk about is that a simple function like the transpiration function, which I have here, for a model which doesn't have interception, might be something like that. And if I compare it, this is the recomputed value. The recomputed value are the values of the transpiration to the potential evaporation. Because I don't have interception, so these two are exactly identical. And if I look at the frequency of when or which part of this basically function is activated, most of the time, let's say 80% of the, or on the average is activated like 80% of the time, means that 50% of the time it's above this value, or transpiring more than a ratio of 0.8 compared to the potential evaporation. However, if I put interception and then I recompute my transpiration, my function will be lost. I don't have a function anymore. And then the frequency also will be lost. And that's again very important, because if I say I know exactly my transpiration, it's Jarvis, my stomatal resistance is this amount, that doesn't matter, because as soon as I change my interception, everything will be changed. So that put under question all the physically based modeling and the strong assumption on the lookup tables and etc., which we already know, but that's a nice way of showing it. And by the way, here we know that interception is maybe 40% of the total evaporative flux, or around 30% of total evaporative, and that is already given. If I wouldn't give that, it would be even more messier than that. And of course, this opens the discussion, because we can also have the entropy of the parameterization itself can be computed. So other implications: minimally restrictive process parameterization can be a medium in which the modelers and experimentalists can better explore and inherit uncertainties in model and exchange knowledge. And we hopefully can create an active role for process-based modeling in the era of machine learning. More importantly, bring the uncertainties, because most of the things I talked about was the uncertainty. We can learn this function, but given the uncertainty, because uncertainty, in my point of view, is what is missing in a lot of machine learning application in hydrology. So in hydrology, we have two main aspects of machine learning. Maybe I'm missing some studies, but I can categorize them in two. So one is making machine learning to approximate a surrogate of more complex model, optimization, calibration, replacement. So we can help the optimization algorithm, for example, to find the better solution, because now we can, instead of just giving the parameter set and output, we can give the parameter set, simulated soil moisture, simulated transpiration, and then make the optimization algorithm more smarter to find the better solution better. Or we can replace, we can do a Monte Carlo sample of the more complex model and replace it with the machine learning, which is probably much faster and perhaps is also easier to fit and calibrate. So that's one thing. And then the other one is linking processes and catchment attribute. This is often referred to as physics, but it's actually not physics. So this should not be processes. This is input, output, and catchment attribute. So we have a input, we have output, we have some sort of catchment attribute, land use, etc., etc. And we try to find a linkage between them, if there is any. But actually in this process, we don't really dig into the physics. By physics, I mean coming out with a universal function that can be replaced, for example, for transpiration, or can be replaced for the subsurface flow. So I just conclude, and I perhaps provide some thoughts for the future work. Process parameterization equations should be treated as conditionally dependent on system architecture selected for a given application at a given scale. That's very also important. Can we go from smaller scale to the larger scale? Can we apply the Richard equation at the larger scale? Because, for example, land surface models are applying approximation of, very bad approximation of the Richard equation just at the grid of 10 by 10. Is that even possible? Most of the upscaling of Richard equation, I think they never went larger than heliotrope scale hydrology. The relative identifiability of PPE form can be strongly dependent on the degree of activation of the corresponding processes, and such activation will rarely, if ever, be uniform across its behavior range of PPEs, and it's dependent on the architectural hypothesis. So that's also important for us to infer when we do the inference, calibrate how the system behaves. So there's more dimension into just calibrating and picking some parameter values. The use of soft information in form of simple behavior constraint and internal model behavior based on hydrologically informed knowledge can help dramatically increase the identifiability of model states and output space. I think that's the most important things that hydrologists should do, to come up with the soft information. There is a lot of room here for improvement. And I think a lot of challenges we have is because we simply ignore it. Of course, we can apply water balance, energy balance, even something like entropy at larger spatial and coarser temporal scale, and perhaps it works. So we would be happy. But if we want those concepts to be applied and much higher resolution, time, and space, we need the constraint. And whatever we do is dependent on those constraints. So we should really formulate them well, and we should really understand what they are doing. And mapping of modeling efforts to each modeling hypothesis and investigating the unexplored scientifically. So by the basically the map that I showed about the hierarchy of the model decision, input uncertainty hypothesis, output uncertainty hypothesis, basically performance metric hypothesis. So we know which part hydrologists are putting most of the effort. For example, I think maybe it's not very nice to say, but the fact that a lot of effort went into like optimization performance and all this discussion of which one is the best, and it was NSC, and then comes KG, and then after KG comes a lot of different discussion on how should we do it better, etc., etc. It's all outside of the modeling hypothesis, and there is much little effort is done into the modeling hypothesis and also the soft information, and how we can talk with somebody, get that information, make a constraint out of that, and put it in the model. Sorry for the long presentation. Thank you very much. Looking forward for the discussion, and hope you enjoy it. Yeah, I finished. Back to you, Leila.
I think Hashim has some comments, or if anybody else has a question.
Shervan, you want to say something about where you're planning to go with this next?
Yeah, actually we can go a lot of directions. So it opens avenue for many let's say practical application of hopefully. What I really like to see is, for example, if we have a simple model, if we have the let's say soil moisture of that a catchment, and also the output of that catchment, input of that catchment, what would be the shape of this function if we impose, let's say, extra data like soil moisture. We have done, if you remember, we have done very preliminary work during my PhD for that, but I think that's a really important step, because if we know what form of function is better than the other, for example, given soil moisture, it will heavily reduce the data assimilation, because data is already assimilated into the process parameterization. So I think that's an avenue we can explore, and machine learning can really help So we can have a machine learning layer on top of it, which basically obey this physical law, obey the conservation law, and yeah, there are a lot of other issues, like how to build this minimally restrictive process parameterization, because that's also an avenue to explore.
Let me just mention quickly. In the early language, we were using the term maximum entropy approach, just because of the community and so on. There was some pushback, and we used this terminology. But in general, the idea was the goal was to try to implement a sort of a maximum entropy approach in terms of the process parameterization representations.
Yeah. And so these are, I think, the question we can try to go after. But what I think is a bigger challenge as community, as a person who am I in the Earth system modeling community, is that a lot of people are not very happy with this type of avenues, because it might be counterintuitive to what they are doing already. So I'm just talking about the resistance, as you mentioned. So we have seen this in the review process. We have seen this even during the discussion with the co-author, because that means that perhaps some of the modeling effort and the strong assumption that have been done over the past years are not as so basically this is another way of putting Gray's paper from 2020, which he mentioned about the role of the process-based hydrologist in the era of the machine learning. I don't know if this was discussed, and I totally understand him, and the sort of frustration comes in that paper, if I hear that correctly, because a lot of assumptions which goes into this regionalization and larger scale modeling are not taken from the data and cannot be really produced by the data. So we are really making ourselves much more constrained in the solution that we should be.
So following on that, an interesting question is, the work that Shervan did was based on using data from single catchment. So the interesting question then would be, if you were to use large data,
yes,
data from multiple catchments, could you dramatically constrain the uncertainty in the process parameterization representations or not?
Yes.
The classical approach through machine learning doesn't teach us anything about what we know or don't know about those process representations. But by approaching this through a hybrid approach, perhaps one could explore that question as to whether that uncertainty can be reduced or resolved by using large data sets.
Yes. So for example, what I meant for the basin and the soil moisture can be done for larger scale, like for MOPEX data set or for CAMAS data set. We have the capability to do that already, so we can explore this avenue as well. Yeah.
Yeah. Hi, can you hear me? Okay.
Yes. Go.
This reminded me. Thank you for the presentation. That was really interesting, and it reminded me of something I read a few months ago on AI Feynman. I don't know if you're familiar with the paper from Max Tegmark last April, I guess April 2020. He discovers 100 equations from Feynman lectures, using a semantic regression approach, just saying, okay, there's a finite number of functions or of operators, mathematical operators, So there's a huge search space to come up with a model, but there's a clever way of exploiting structure in how models are typically, or in known equations are assembled. And so it's so, combining machine learning, but I think there's somehow, physics is somehow incorporated as well. But anyway, it just seemed like I saw a similarity between what you're presenting.
I would be happy to see that paper if you can share that with me.
Yeah.
Yes, part of the issue that we had writing this paper and also during the review process was a lack of really relevant paper in hydrology that are talking about this in such a broad level, which I think is quite normal for other fields, specifically physics, but somehow it's missing for hydrology. And yeah, that's just makes me think like what laws we can learn in hydrology.
I think the other really interesting part of this the way this was presented is it presents it as the results. It's searching a space of models, and then it presents a Pareto optimal front of accuracy versus complexity.
Yes.
So you decide where where
exactly.
you want to be on that curve, and in a number of these cases you have this very well defined corner. And that's it. It's really nice. I'll forward that to the group.
Yeah. Oh, thanks, Hoshin's on this.
That's a different one by the same guys. It's not exactly the A.I. Feynman one, but it's an interesting related paper. Yeah.
Okay, can I ask maybe a broader question? I'm trying to phrase this appropriately, and I don't know if I am going to say this correctly. But a lot of the times when you are thinking about the model and the way you characterized it, it was very process oriented, right? So you add remote processes and think about what the sensitivities are. But when you're developing models, a lot of the times you're thinking about a phenomena. So flood is a phenomenon, drought is a phenomenon, right? And so evapotranspiration is a phenomenon because it involves many different processes. And there is a big jump between thinking about a phenomena and thinking about the associated processes, right? And when we are characterizing the error in prediction, oftentimes we are too caught up in the error associated with a particular process rather than how well did we do with the phenomenon.
Mm-hmm.
And analyzing the structure of the error as to why something does not go well is just as important as why something is going well. So where in this iterative loop is this idea of looking at the structure of the error and helping that formulate a hypothesis, which might give rise to alternative formulations. That's one aspect. And this applies to phenomena that we may have already observed, right? A lot of the times models help us anticipate phenomena which we may not have seen.
Mm-hmm.
Right? And so, for example, in our critical zone project, during discussions, we put forward 2 or 3 different things that may happen. And then we go and look at the model and say, well, the model is saying that this A is more likely to happen than B or C. But sometimes the model should predict things that we may not have seen before, right? So where in this thinking do we allow the models to do that?
Mm-hmm.
And where does it come? I mean, when we make it too data-driven, it essentially says, well, everything is in the data, but everything may not be in the data, right?
Yeah.
And we're trying to get to models which mimic reality, right? Whatever your perception and conceptualization and so forth is. I mean, the example I like to give is in physics, where they predicted gravity waves based on theory 100 years ago. It took 100 years for technology to catch up and put LIGOs and observe that gravitational phenomena, a wave which is smaller than the size of an atom,
Mm-hmm.
right? Where are we doing those kind of things in our hydrologic thinking? If you're going to advance the science, I think we have to allow for these things we may not have seen. For example, under climate change, we may see phenomena which we have never seen before, right? I mean, the CO2 levels in atmosphere are at a level we've not seen in over 5 million years on the Earth. And that is certainly going to give rise to phenomena which we have not seen. So how do we accommodate that in this way of thinking that you're presenting?
Yeah. Hoshin, you want to say? I have some thoughts. Sure. Yeah, go ahead.
So you completely, I think you put your finger on it, Praveen, that we tend to be, when we look at models for historical reasons, we tend to think of models in terms of the errors point by point. On the, you have an observed stream and you look at the point by point stream. At least some attempt to shift the thinking in that direction that you're talking about was the discussion about behavioral processes or behavioral models, which was brought up originally by, what's the gentleman's name? Shervan, in the context of sensitivity analysis originally. Anyway, which actually led to glue and some of the other techniques. But from our side, we basically started to say you need to look at signature properties of the data. In other words, you don't look at the data one by one, you actually look at patterns that are in the data. So that was sort of an attempt to steer the conversation in that direction. I think the work that Shervan did in this paper, he's using metrics, point metrics to measure performance. But I would completely agree with you that we should be not equating data and information. There needs to be some mechanism by which we look at patterns in the data and extract those. We call them signatures, and think of those as the underlying patterns that we're trying to reproduce rather than specific data values. It's interesting, however, I just reviewed a paper, I believe it was for WRR, where the authors attempted to bring an approach like that to machine learning, where they were evaluating machine learning models in terms of whether they were behavioral in the sense of were they generating sequences that had behavioral patterns that were consistent with behavioral patterns in the data, or that were consistent with behavioral patterns that theory tells us to expect. In some sense, what Shervan did by putting constraints internally on the states and parameters and so on was an attempt to reflect the kind of thinking that you're talking about. How to take this further into things that we have not yet observed, I think is an interesting question, because you can only test the model on things that you have observed. But presumably you need your evaluation procedure to not reject a model based on things that you haven't observed.
Well, we are doing this in our critical zone. I mean, we are using models to predict things so that we may design experiments to see if that is what it is doing. And then it'll be an iterative process, because we will certainly be off from what the model is predicting, because we have not seen the phenomena yet. We're speculating on it. And so the parameters that we're putting in the model are our best guess, and they will be revised and so forth. I think probably this question also sets the stage for our next discussion on counterfactuals, right? I mean, essentially things that are possible, but we haven't yet seen, maybe, and how to think about those.
It's sort of interesting. It's sort of interesting, Praveen. I think that when we first started building computational models, people were using them as tools for understanding, right? And they would look to see that the models gave the right kind of behaviors, and they were not so concerned about whether the numbers were exactly correct. And then we went down this track of calibration and tuning, because we got involved in prediction. And now you have this interesting debate about whether a good predictive model represents good understanding or not, and vice versa.
Yeah, and I think this has come around in the loop because of the idea of complexity, right? Because when you are predicting, and if you're predicting one variable at a time versus whether you are predicting the interactions between these components as a whole, which is what will constitute a phenomena, then that is only possible through simulations in a big way. But we have never developed metrics for those kind of characterizations.
Yeah.
And in fact, in some of our early multi-objective work with land surface models, you could show that you could tune the model to a specific flux and make it perform extremely poorly on some other flux, because there was poor representation internally in the model. And then you could tune it on the other flux and it would become really poor on this flux. And so the fact that it was performing well on the data was not actually a guarantee that the model was performing consistently internally, which becomes an interesting challenge.
Maybe I can add from the experience I had with let's say simpler model and more complex model. I think what you are saying, or the dimension of what you are asking, is much higher than the formulation of the process and the parameters in the model. And I think that should be acknowledged. And so even if that process, that parameter we have there, maybe I can share my screen. And, can I? Yeah, I can go back to the presentation. Where was my presentation? Just a second. Share screen. Yeah, here. So I can just say quickly with very simple models. I just skip over all this. Again, we are coming back to the model. We are not really answering your question, Praveen, but let's say I have a very simple model and I have a very complex model. And I know a lot of things about the relative parameters. So there can be two approaches. There can be an approach where it says, I know exactly what this parameter of the interception is here. This is what we do in the land surface model, the multiplier of the LAI, for example. But then I can also relax that and say, well, I just know exactly what it is. Even if I know LAI, I know what's this, it's relational value. So I can come up with this type of relaxed assumption, which hopefully some of those solutions in the future, which I don't see, should be conforming with this simple constraints. But so they are process constraint, and they are basically parameter constraint, and they're process constraint. Like we can put in the dry period. This is like drought that you mentioned, or flood. In the dry period, I want this to be more than this, and in the wet period, I want the opposite way, because hill slope will be activated. And every solution which satisfies this is okay for me. But the problem is that if finding that set of, this is a paper that we published in 2014, finding those uncalibrated but constrained parameter sets, it's very difficult because this space is very small compared to the initial space. And to what I have seen is that marginal distribution of each parameter doesn't explain this. So it's a space with perhaps a lot of holes, with perhaps a lot of abrupt changes, because it's just calibrated on those really rough constraints. But if I can find this in this space, there should be some of those solutions that you are searching for. But how I make sure that whatever I found is really this uncalibrated but constrained, how big is it? That's a very difficult question. And often what we do as often what experimentalists usually do, let's say, is that they come up with only one solution, which perhaps is here or maybe even here, and they're satisfied with that. But actually that solution is just one of millions.
Sorry, go ahead. Sorry, go ahead.
Yeah, I just wanted to say that then we can, of course, calibrate and constrain, but this calibration is again projection into that. But what I just wanted to say is that I think what you're asking is about things we did not see should perhaps be in this space if the constraints are developed in a way that are agreeable, they can be held in the future, and they are not really subject to change over time. And the relative space of this red to the blue will explain how much information they bring and how much plausible solution which we have. Yeah.
Yeah, no, I should Dan has his hand up, but I'll just make one comment here very quickly. I think I'm not focused on the parameter side of the story at all. I'm focused on the process side of the story. I think if you're missing a process, you're going to force a parameter to take the fall for it. Yes. Whereas, the right thing to do would be not search in the parameter space, but in the process space. Are we missing a particular process, right? Yes. So there is going to be a continuous trade-off associated with that. A lot of the times, what are parameters are actually processes at a slower time scale. So porosity, as an example, is essentially development of soil from a particular underlying bedrock material or others, and that porosity develops as a result of a certain processes acting over a much longer period of time. So that's a big parameter space. The whole hydraulic conductivity story and stuff like that is essentially a process space, but because we are running simulations for a month to a year to a decade, that's not changing. But if you have to run for 1,000 years, you better account for that as a process and not a parameter, right? So there is a whole suite of those questions in there. So anyway, that's an interesting debate. Dan has his hand up for a long time, so I'm going to let him speak.
Thanks. Well, this is actually a question for you, Dr. Kumar, to follow up on your point about the gravitation or gravity waves that were detected. So is there a difference? You're saying, is there, what are, we haven't arrived at these in hydrology, but are they happening? Or, are there, is there a distinction between the process that that these gravity waves are being generated, right? Those are fairly common, aren't they? It's just that we haven't historically had the means to measure them, right? So those it is collisions of black holes, right? Is that what's causing the waves that are being measured ultimately? So those are actually not that uncommon, but how does that compare to the systems that we're interested in? That's my question.
Well, there is a phenomenon of all kinds in hydrology, which we generally tend to not account for, right? I just mentioned one, but for example, you build a new city. I mean, that cities are expanding. So a river flooding downstream of a city, that pattern is changing. The chemistry of that stream is changing, right? We always, in hydrology, unfortunately, we're always talking about floods and drought, which is essentially, in some ways, extremely limiting in our thought process. But if you look at, say, example of stream chemistry, emergent pollutants in there, those are new phenomena. I mean, you're finding microplastics in the rivers downstream of cities, right? So those are potentially new observations which you probably haven't done. But could somebody think about those things saying, hey, I mean, if these things expand at this rate, here are the new things that will emerge. These are the potential consequences of these, right? And then suddenly you find over that happening. Climate change related stuff. I mean, if the patterns of rainfall, the persistence of rainfall is going to change, you're going to definitely see these new phenomena. And that has been documented, right? Persistence of heat waves and cold waves is changing. And those are good. Persistence of heat waves are going to drive all kinds of hydrologic phenomena, evapotranspiration and so forth. So they are happening and they will continue to happen. The question is, do we have the components in our model robust enough to be able to predict that in there? And it's always this evolution of interdependence that is creating these kind of components. So in our models, we tend to have these interdependencies locked. The equations define what we are coupling, and then the way we couple them is completely locked in, right? I mean, the only wiggle room we have is the strength of the coupling, but not going from 0 to 1, right? Or 0 to non-zero, so as to say. And when you go from 0 to non-zero, that's when you see these things emerge. So how do we think about those? I think that's quite not there yet, or at least not well articulated.
So just to say that we tried to think in that way that you are saying in a very limited fashion in this study. And that is exactly the interconnection of this assumption that we make in our model. So if you, let's say, come up and say, well, there will be these small particles, the plastics, we can put that into the model somehow, not very strong, and see what would be the output solution. But yes, as you said, as we showed, there is a lot of room for finding this interaction, let's say.
Yeah, my point was not being to be critical of what you were presenting. My thought was that there is more expansion space to be. I think that's a space to think about. All right, and Andrew has his hand up.
Yeah, thanks, Shervan, for the talk. First of all, I think it's really cool work, and I actually agree with a lot of what you're saying, especially the sort of, we throw calibration at an existing model and call it good. And I think what you just said was something I was going to ask about, so you kind of cleared that up. But that, I guess, the idea that you can kind of start with your sort of whatever building block processes you want, and then figure out some constraints from it, and kind of come to different models that way. So I guess part of my question is then, do you have a sense of practical ways that we can do this with real data from different sort of, because Praveen was just talking about droughts and floods and stream chemistry, and those are kind of two very hard to compare things. Do you have a sense of how you could incorporate both at the same time?
That's an excellent question. And I think we have to go slowly to get there. And that was what I mentioned. Like the first other step can be just, instead of just putting this minimally restrictive, let's say combine this with the machine learning, like what we have done in your paper, but let's say combining it instead of helping the optimization algorithm, and see what would be the transpiration function, for example. It might be possible, for example, through SUMA or much simpler models, but it's quite challenging, I would say. We can address it slowly by slowly, but I think there is a lot of, I mean, probably where we are now is like when in the beginning of 90s, they said, okay, it's parameter uncertainty, and there was a need for optimization, and then SC come, and then MOSCAM come, and then a lot of other optimization come. So probably we are at that point, which we are going slowly. Maybe I also don't have a good understanding of how it will go. I think future will say. But there are thoughts to start the small steps. If you have any, I mean, we can have a discussion on that. I mean, what do you think? Because you have been doing process-based modeling with machine learning. So what is your vision on that?
Yeah, I mean, I think you're right. It's hard, and I don't think anyone really knows how it's gonna, how these sorts of things pan out. I mean, historically with process-based models, it seems, you know, people took, you know, bits and pieces of sort of best understood experimental or empirical stuff and just threw it all together. And I think the hard part is with some of these more sort of like emergent approaches, rather than taking existing building blocks, is making sure that pieces are actually able to talk to each other meaningfully. So I think that's the approach that I would like to see first, is someone to kind of figure out how to make stream chemistry inform floods or droughts, but I don't, in a way that's kind of generic. I know there can be like some studies done, but from a modeling perspective, I don't know.
Yeah, well, yeah, me neither. But what I just suggest is that let's start simple. Let's say, can we do it for transpiration and tower fluxes? And why transpiration? I mean, probably you know the work of, it was not published, but I'm sure you know the work with Bart and Martin, and why these models like SUMA or land surface model, well, not SUMA, but the formulation, let's say, are for the transpiration or other evaporative flux, they are not as good as they should be. So we can maybe start from there to see what's the issue. Can we find a universal function like Jarvis, which can be replacing Jarvis, or can be replacing Ball and Berry formulation? Because it's looking at those formulation and the way they are formulated, they're scary. The assumption which goes there, I don't know, the denominator of the vapor pressure deficit is 4 kilopascal, no matter for the entire planet, for the entire vegetation. Somebody measured it in prairies of Kansas. Yeah, so I think there is room. I don't know how do we go, but let's do it small. And I would be happy to have a discussion and maybe further collaboration on it. Thank you. Hoshin has maybe interesting.
So Praveen, your question reminded me of this thing which is sort of uppermost on my mind all the time now when I'm talking with my students, is this idea that the representation we use completely determines the questions we can ask, the answers we can get, and the analysis that we can do. And so I think, in a sense, I'm reframing a question in terms of that truism or insight. And I'm reminded of when I was reading the Mars trilogy, where sort of the model, the metaphor was of the scientist who basically sat down with his personal assistant, intelligent agent, and he wanted to study a problem, and he basically would ask a bunch of questions to his computer, and the computer would go off and look for data to try to help him, understand that. So he's doing a process of discovery, and then he'd be thinking about his problem, and he'd look for data sets and try to answer the questions that he was being motivated or driven by. And so this brings me to the thing of how do you use models as tools of discovery, right, as opposed to something else, which is an interesting and challenging problem, because you start with some data sets and you try to explain the relationships in those data sets. And we tend to focus on the things that are the strongest predictive patterns in those data first, typically. And we ignore the ones that are not consistent with those strong patterns, very typically. Whereas, so that event might have happened only once in the lifetime of your data set, or something like that. But that might, in fact, be the one thing which you really care about. But if you're focused on demonstrating how good your model is, you're going to ignore that one. Whereas if you're really focused on trying to understand how the system behaves under many counterfactual types of situations, it's exactly those patterns that your model is not explaining well, the ones we want to focus on. But that's not. So that's the difference between treating a model as a tool for discovery versus treating it as a model for prediction.
Yeah, I agree with that. I mean, I keep thinking whether the models always require data. Okay, let's not go there.
I would say they always need forcing.
No, you can develop theories without data, and theories are models.
Okay.
And not your computational models.
Yeah.
But
well, let's say time step models, they always need some sort of.
No, but I mean, I think what Praveen is talking about, things like Newton's laws or whatever, the idea that they were developed without data is a little questionable to me. But whether they are exact representations of data is a different thing. Yeah.
Yeah. So let's take Newton's law as an example, right? It's the inverse square law. If you put the power to anything but 2, 1.99999, it does not work. Mm-hmm. Okay. There is a reason why it is 2 and not 2 plus minus epsilon. And any machine learning approach is not going to give you 2 as your best guess given whatever data you give. It's going to come up with some approximation. And
with an exception of the recent Wu and Tegmark work on AI Feynman, which is especially dedicated to that thing. Yeah,
that's forced learning over decades, right? But the point, you see my point. I mean, the thing is, if we extract ourselves out of this and data drive it, we are not getting to, we may get predictions, but we are not getting an understanding why it is 2, and not being a 2 makes a difference, right? And so I think it's that kind of a thinking that we need to be going and pushing for, right?
Sure, but I mean, I would really like somebody to explain to me how one could go about sitting down at your computer and just looking at the data and starting with that and emulating or learning from many generations of human beings' understanding of how to do discovery, right? With data sets, can we construct support system architectures? Maybe some of the things that are there already along those lines, where you're not so tightly constrained by some of the main assumptions that we're being forced to make, but you're being guided by them, right?
Right.
Guided by principles rather than by strict requirements. I mean, right now, what do you tell your students? You got some data, you got 2 data sets, plot an XY graph, right? So, if your X and Y data supposedly one explains the other, and you get a big cloud, then you postulate another latent variable. So these are the kind of insights that people have sort of. That's what you go to school. But you don't actually see a textbook telling you how do you, do this, then do this, then do this.
But I'm just maybe I'm not into a lot of reading these days, but I have a little bit of issue with model being formed without any data, because somehow this data should be somewhere, or something should have been learned from those data in the past, or something that these theories pop up. So
I think we're getting into a language problem here. Praveen was using the term phenomenon to represent an abstract thing which is based in perceptions. And what we call data are the projection of the world onto very, very specifically designed machines to make measurements of very specific kinds, in time and space and so on. So one would have to discuss that continuum of where you go from phenomena down to what you actually measure, right? Which is an interesting journey in itself.
Yeah, I don't remember if E is equal to MC square was based on a data. I'll have to go and look whether there was actually that kind of a measurement before that particular formulation was launched, right? Or for that matter, the entire quantum mechanics, the Schrodinger wave equation, was not trying to fit data in there.
Sure.
It was trying to explain phenomena, saying, okay, we know this is what has been going on. This is what we know. Of course, that is coming from data, but it's an abstraction of the data into phenomenological expression and saying, okay, now this is a possible explanation as to what's going on, right? So it's that kind of a thing in there. So it's not this data driving this outcome, but an aggregation of thought process that drives the development of the theoretical foundations.
Well, an example of that would be a mathematician working with mathematical symbols, right? And principles and rules and so on. For them, their data set involves, that's the problem with the linguistics, is what I'm trying to say. The data set might involve a set of mathematical symbols and a set of theorems and a set of things, all of which have to be maintained as consistent, as opposed to saying temperature, pressure, and volume have to be a constant under some, right? And you got actual. The question is, what are the things that you're manipulating and trying to extract information from?
And I think that we're probably over the time limit here, but I think that leads to interesting characterizations of this information of knowledge and our relation between information and knowledge, right? So basically, knowledge is hardening of information. You learn something and you convert it into. So your computer is essentially an accumulation of decades of information converted into knowledge, and then you can construct something which is in there. So how do you go about hardening that? So there is a whole suite of these discussions that need to happen. When you think about this, we always think about the phenomena in nature, and computers, for example, do not violate a single law of nature, right? But nature by itself would not have arrived at creating a computer the way we see it. So perhaps the way for nature to arrive at developing a computer is to develop an intelligent being who is then capable of developing a computer, which is all consistent with the natural phenomenon. So how do we think about all these things in a coherent manner is an interesting philosophical discussion, maybe a little bit out, but also probably pertains to thinking about information and knowledge and so forth. So,
well, this is going to come up in the book on can and can't, isn't it?
Yeah, it'll come up in the next discussion.
So I during the process of this paper, one of the reviewers, which is I think he's from ecological background, he used the word tacit knowledge. So he said this paper might be a way of exploring tacit knowledge, which we usually put in the model, depending on where we are coming from. But how do we, why as a modeler, I'm modeling the way I am modeling? How do I measure this? Where did this knowledge come from? Why I would be different from another person? And quantification of that, I was thinking, would be probably very difficult. I don't know, I'm just interested to know your thoughts on that.
So we've probably gone way over.
Yes, but it was a really nice discussion. Thank you, Shervan, for a great presentation and for the discussion. And I want to make some little announcements. So this is also a quick reminder of our next session. So it's going to be on June 30, and we are going to be discussing the book by Chiara Marletto, The Science of Can and Can't. So it takes a while to read, and I also found out that there is an audiobook, so if that helps you to read the whole thing, is very beneficial. And also we have our wish list for our next readings, and we need to revisit that to decide what to read for July 21st. So if you have a preference and if you are willing to present, just let me know. And I think that's all.
Eli, if I could just take 1 minute, I sent you the revised version of the paper.
Yes.
And if you don't mind, I just want to share the one image so people can see the nice result we got finally. If you can see this, just to point out that one of our reviewers insisted that we test our method against kernel density method. And so we ended up generating this plot, which basically shows sample size on the x-axis, 4 different distributions, the deviation from true entropy. And what we're comparing here is the quantile spacing method, the kernel density method, and the bin counting method. For the bin counting method, we have to optimize the bin width by maximizing the likelihood of the data. For the kernel density method, we have to optimize the kernel standard deviation by maximizing the likelihood of the data. And for the quantile spacing method, we just fix the number of quantiles at 25% of the data sample size, as we talked about last time. And you can see we got a very nice result, which showed that even at very small sample sizes, the quantile spacing method gives relatively unbiased estimates of entropy. This, by the way, the y-axis is, you can interpret that as Kullback-Leibler divergence, or scaled Kullback-Leibler divergence. Whereas the kernel density method can give you up to 10% bias, and the bin counting method is really poor at small sample sizes. You can see that you get 50% or more. So anyway, this is just, I just thought there's a lot of technical stuff in the paper, but this one is the sort of final one, which basically shows you why you should use quantile spacing rather than another approach. Yeah. So thanks for letting me share that.
Yeah, absolutely. And once you do it for multi-dimensional ocean, that'll be great.
Yeah. The next thing we're working on is to first test it on do exhaustive testing by manufacturing all kinds of weird shaped PDFs, which have discontinuous derivatives and so on. So we're going to do exhaustive testing of the different methods. And now I'm starting to think about how we can extend that to higher dimensions. Thanks, guys.
Okay, thanks.
Can I quickly ask you a question? So are you planning to discuss this book, The Science of Can and Can't, that counterfactuals, in one session, or like it's going to be more than one? Like it should be more than one, right?
Well, we'll do a presentation, and then we'll have to see how much extensive discussion we want people to do. So right now we're just planning it for one, but let's see how it goes.
Yeah, ideally it would be great if people just purchase the book and read it, and then we had a discussion rather than trying to summarize what's in the book. I think that's going to take a long time, but the discussion will be quite interesting.
Sure.
Okay, bye.
Okay, thank you, everyone.
Bye, guys.
Thank you very much.
Bye.
Bye.
Great job, Shervan.
Thank you.